All right, welcome back. Today we're going to go over some linear algebra notation and just make sure that we're on the same page in terms of linear algebra on the basic concepts before we get into the real meat of this class. Okay, so let's get started. First thing, let's talk about vectors. So in this class, we're going to use lowercase letters primarily, could change, but lowercase letters as vectors. And vectors, we'll always consider vectors as column vectors. So here we have vector, and it's a column vector, and it has scalar elements. So this vector is of length n, and the notation I'm going to use to say that it's of length n is this notation. X is in Rn. Okay? So this is just a shorthand notation, mathematical notation, and you'll get used to it if you haven't seen it before. But X is your vector. This symbol means in. And R just means that each element, xi, so any of these, each element is a real number. Okay? Is a real number, and there are n of them. Okay? So a very shorthand notation to say that X is a vector of length n with real numbers as the elements. Okay? So you'll see this again with matrices. Another concise way to write a vector is also X is equal to x1, x2, ... xn transpose. Okay? So that's still a column vector, but just to save space, in many cases I'll use this notation. So if you see a row and with a transpose, then you know it's a column, and that's our vector notation. Okay, so let's see what we can do with vectors. Let me ask you how you would add up n numbers. Okay, so you've got some, let's say you've got some list, and in other words, or a vector. So I've got this list, and 1, 2, 3, ... to 49. Okay, that's our list. And I want to add all of these numbers together and find out what the final value is. How would you do that? All right, so for me, 3 different ways come to mind. Okay, so let's talk about option 1. Option 1. Option 1 is to use a built-in command in the software that you're using. So for example, built-in command. For example, if you're using Excel or if you're using MATLAB, there's a command called sum of x. And if you just type this into your console, it'll give you the solution. So you basically don't even have to know what's going on underneath the hood. That's one option. Okay? Another option is to understand what's going on under the hood and use write your own code and use a loop. So for example, let's write some pseudocode. I would start off and I would define a variable known as sum with a capital S, and I would initialize it as 0. And then I would do a loop. So for ii equals 1 to n. So, or the length, sometimes you can use a function, built-in function known as length to find out the length of your vector. And I'll do this n times, and I'll re-evaluate or evaluate the sum by adding the previous value of sum to the element the current element of the list. Okay? And that code right there will add up, start out with the sum equals 0, then it will take 0 plus 1, loop, 1 plus 2 gives you 3, and you will continue the loop. Okay? Now, the third option is going to be the one that I want you to pay attention to more, because this is the way we're going to use linear algebra notation. So I want to show you a linear algebra way of computing the sum. Okay? So first while I'm doing this, I'm going to define the inner product, or also known as the dot product or the scalar product. All right? And this is it. When you take a row times a column, you actually get a scalar. Okay? So now the interesting thing here, one thing to note, and this actually becomes useful, is that as you can see, since it's a scalar, if I take the transpose of a scalar, I get the same scalar. So if I take x transpose y transpose, that is going to be equal to y transpose x, and it doesn't change. So they're both equal to each other, and that's a neat trick, and you might find it useful later on. Okay, so let's look at this. So this would look like this: x1, x2, dot, 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 xn, multiplied by y1, y2, dot, 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 yn, and that's going to be equal to x1 times y1 plus x2 times y2 plus dot, 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 xn times yn. Okay? So, now that I've defined the inner product, let's see how we can take the original x from the last page, okay? So let's, and use the inner product to produce the sum, okay? So I think if you sort of look at this, you can see that if my y's were all 1s, then I would actually get the sum of x's, okay, the sum of our list. So let's try that. So if I write that, I would write that like this. So sum of x would be equal to x transpose and then transpose with a 1's vector, and I'll define the 1's vector as just, so here's x1, x2, dot, 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 xn, sorry, no transpose there, times 1, 1, dot, 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 1, and that will get you the sum of your xi's for I equals 1 to n. Okay? So that's a useful tool. So remember the 1's vector. That'll definitely come up a lot in this class. And the inner product will come up a lot also. Okay. Now, let's move on to matrices. So here's a matrix, and again, a shorthand notation to say that this matrix is an M by N matrix, and another shorthand notation would be A is in R M by N. Okay? So again, it means that our elements are real numbers, and this again is just the mathematical symbol for in, and it's an M by N matrix. All right, so I'll use that frequently. There's nothing tricky about it, just the shorthand notation. All right. Now, let me show you two other ways to write matrices. This is an element. This is element by element way of writing a matrix. Let's look at instead of element by element, let's look at a list of rows and columns. So let's look at rows. Okay, so I could write A as, let's call this A1 transpose. So A1 is the first row, or A1 transpose is the first row. A2 transpose is the second row. And dot, 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 AM transpose is my mth row. Okay? And that would be, this would be AM. All right, and I'll show you in a second, this notation can be useful, so I want you to be aware of it. And then let's look at, instead of list of rows, let's look at a list of columns. Okay, so let's rewrite A. Now write A as, and I'm going to call this A1 hat, just to make sure that it's different than A1 here. A1 hat, A2 hat, dot, 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 AN hat, because there are n columns. Okay? And that is another way to write the matrix A. All right? So I just want you to be aware of these three different notations, and you will probably see them. Okay. So now let's combine what we've done so far and try to write out what AX equals B. Okay? So AX equals B, well, first of all, what this is basically M simultaneous equations and N unknowns. So let's look at this. Let's write it out. So the first equation, so this would be equation 1, A11 x1 plus A12 x2 plus dot, 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 A1n xn equals B1. That's one equation. And then let's just go down to the end. Equation M has AM1 x1 plus AM2 x2 plus dot, 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 AMN xn equals Bn. And of course, sorry, B is actually Bm. That's a typo. That's an M. So here all we have is we're basically looking at M equations and unknowns. All right, and maybe one of the questions is what x's will solve these M equations. All right. Now there might be no solutions, there might be an infinite set of solutions, or there might be one solution. Okay. So let's look at this a little bit further, but I want you to be aware that when you see AX equals B, that is M equations with N unknowns. All right. So I want to rewrite, so I talked about the row and the column notation of the matrices. Let me write AX equals B in those notations, just to show you how I would do that. So here, let's do the row notation. Okay. So here I have, and I'll rewrite it, A1 transpose and AM transpose. And actually, I'm going to leave this out and just call the vector X, and equals B1 dot, 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 BM. Okay? So I'm going to write this, and now I can multiply. This is an inner product between A1 and X. So what you get is A1 transpose X and A2 transpose X dot, 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 AM transpose X. Okay? So this is another way to write AX equals B, or more specifically, AX can be multiplied together to give you this. All right? Let's look at the column notation now. So the column notation would be, so you have A1 hat, dot, 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 AN hat. And now I'm going to, on purpose, write x1, x2, and you'll see why in a second. Xn equals B. Okay? So if I write that, this is like the column A multiplied by a coefficient x1 plus A2 times coefficient x2. So let me write that. So x1, that's a scalar. Now the A1 hat is a column vector, plus x2, another coefficient, A2 hat, plus dot, 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 xn times the final column, AN hat, equals B. Okay? So a slightly different way of looking at, three different ways of looking at it, the row, the column, and the element by element. And hopefully you can see the manipulation, because at some point you're going to be doing a lot of manipulation, possibly with columns, possibly with rows. So I just want you to be aware of it. and keep this in the back of your mind and come back to this if you need a refresher. Okay. So now that we have, as I was saying, we have ax equals b, meaning we have m equations, n unknowns. The question is, can we find a solution? So what are our unknowns that will solve ax equals b, that will solve these m simultaneous equations? All right, there's a couple situations. So first of all, again, I define A as a matrix of m by n, B is a vector of length m, and x is a vector of length n. And x are our unknowns, A and B are given. So, well, first of all, we have to decide is what kind of a matrix is it? So first of all, let's start with the simplest. Is it square, meaning that the dimension m and n are the same? So it's a square matrix. Well, that one's an easy one in some sense. I'm going to make one assumption before I write the solution, which I'm sure you're already ahead of it. I'm going to say that A is full rank. Okay. So what I'm going to say about this, without going into too much detail, is that what full rank means is that the rows and columns of A are linearly independent. Okay? So linearly independent, meaning that all of the equations, the way to think about it is all of the equations actually represent something different. All right? If they were linearly dependent, then one of the equations is really just a combination of the other ones, meaning it doesn't bring anything new. So in most cases, at least in our class, we're going to deal with, in many cases, we'll deal with where all of the equations at least bring something new. Now that's generalizing, but let's work with that for now. Okay, so now why do we want to say it's full rank? Well, by saying it's full rank, we are able to invert it. So that means it's invertible. I feel like I need word at this moment. Okay, so now that it's invertible, then the solution is x equals A inverse B. Okay, and we're done. So that was assuming it's full rank, it's invertible, then we can do the following process. Now, of course, if A is very large, there might be some numerical issues, which this class is not about, but I'm just assuming it's a fairly small matrix at this point, and we can just take the inverse, as we had learned in linear algebra. Okay, so now let's look at the two other cases. Okay, the two other cases are where it is not square. All right, so let's look at the first case. Let's say m, meaning the number of equations, is less than the number of unknowns. All right, so if you think about it, you have more, since x, the number of unknowns, or x, think of them as tuning parameters. So I have more knobs, more tuning parameters, than I do equations that I need to fulfill. All right, and this is known, of course, if m is greater than n, it looks like this. Here's m, here's x, and here's b. And sometimes we call that a fat matrix. And also it's known as underdetermined, meaning, again, it has more tuning parameters, more unknowns than it does equations. All right, so that's going to be interesting. Now, the other case is where there are less unknowns than there are equations. So in this case, there are less knobs to tune, but more equations to fulfill. That becomes a harder problem. All right, and this is a tall matrix, so it'll look like this. So this is A, B, A, x equals B. All right. So in the what I want you to know is that, and you probably, if you think about these two cases, especially, let's talk about the underdetermined, all right, so you have more unknowns than you have equations, then it turns out that in many cases, not all, but I'll say in many cases, you have actually many solutions. Okay, and we'll talk about that shortly in a lecture coming up. And the tall matrix, which is overdetermined, meaning you don't have enough unknowns, then in many cases, now I won't say all, but let's just say in many cases, there are no solutions. Okay? And this actually leads us to another lecture, least squares. So if you think about least squares, you've all seen it. You want to fit a line through endpoints. In most cases, unless the dots are perfectly in a line, which is not really, I would say, a useful case, then you actually can't fit a line through all endpoints. All right? So keep that in mind in the coming lectures. All right. So let me finish up with 3 important norms. All right? And when I say a norm, especially these 3 norms, what I'm looking for is I'm looking for a way to compare vectors. Okay? So how do I know, is this vector better than this vector? Remember, we're talking about optimization in this class. We need to be able to, some sense, compare solutions. All right? Especially if there are many solutions, as I had said in the previous slide. So what I want to do is turn a vector into a constant. Okay? So how do I do that? Okay, so how do I do that? Well, I use these norms, all right? So let me define these 3 norms. And let me start out with the L2 norm, or known as the Euclidean norm. So the L2 norm, so I'll box these out for a second. L2 norm is written as this notation, or in many cases, the L2 norm is also if there is no subscript 2, then it's considered also the Euclidean norm. All right? So let me define what this Euclidean norm is. So that is actually equal to x1 squared plus x2 squared plus ... xn squared square root. All right? Now, so as you can see, it took a vector, and it added the square of each element, and then took the square root. That is a scalar. So it took a vector into a scalar. Another way, sometimes in many cases you'll see a squared on top of it just to get rid of the square root. Okay, but it's still the same thing. It sometimes simplifies the math a little bit. Now also, we can write this as an inner product. Now if you can see, remember what an inner product does. It takes one vector element, multiplies it by the other, and then adds as such. In this case, you can see that it's multiplying by itself, so it's going to be the inner product with itself. So x transpose x is equal to the 2 norm squared. Okay? So keep that in mind. And that is the L2 norm. All right? Now, let's talk about the L1 norm and the L infinity norm. So the L1 norm is written as such, x with a 1 as a subscript, and that is equal to the sum of the absolute values of the elements. Okay? Again, taking a vector and turning it into a scalar. And we'll look in future lectures a little bit closer at why would you choose an L2 over an L1 or an L infinity. And the L infinity norm is equal to the max of the absolute values of each element. Not Euclidean norm, it's known as the Chebyshev norm. I forgot how, believe that is probably wrong, but let's assume I can't spell. And so this is not the Euclidean norm. As I said, the Euclidean norm is the L2. Thank you. Okay. I hope that was a good refresher for you, and see you next time.